later on. Good afternoon, everyone. I'll be discussing on constraint sampling and counting. I'll describe what these two exactly mean. I've been giving talk every fall semester, so the definitions will still be the same. I'll discuss somewhat an unlikely path we took where, motivated by practice, we landed on interesting theoretical problem and came up with an algorithm that would not make a lot of sense in the first place if you just think about problems theoretically, but then it actually improves state of art algorithm and performance. So let me start with the basic definitions of the problem. In this talk, I'll be concentrating on Boolean formulas that are represented in CNF form. CNF is conjunctive normal form. There are clauses. They are joined by a and inside every clause, the variables are joined by or. So very simple high school algebra. I'll be using F to denote CNF formula. RF is the solution space of F. So for example, if F is A or B, then RF is 0, 1, 1, 0, 1, 1. So here we are interested in assignments of A and B that satisfy the formula F. Okay? So just to make sure all of us are on the same page, if both A and B are false or 0, the formula is not satisfiable, so there are 3 satisfying assignments. So the problem of constraint sampling is to take a formula F as input and output a solution Y that belongs to the solution space of F, that is RF. Here we are interested in 2 kinds of generators. If a sampler is uniform generator, it guarantees that for all the solutions in the solution space, every solution is output with equal probability. So if we have RF number of solutions, we want to guarantee that every solution is output with 1 by RF probability. In case of almost uniform generation, we relax the definition by giving lower and upper bounds on the probability of generation of a solution Y, so 1 plus epsilon vector. In case of constraint counting, again, to start with the same formula F, we are not interested in generating solutions, but we are interested in counting the number of solutions of F. So, which implies that we are interested in the cardinality of this set RF. So here we have 3 satisfying assignments. We'll be focusing on what is called probably approximately correct counters, which take the formula F as input. Then the tolerance parameter and confidence parameter delta are inputs, and a pegged counter is supposed to output a count C, which is within 1 plus epsilon factor of the exact count with confidence at least 1 minus delta. So we'll be interested in designing counters, where as you will see, and sort of expected that the runtime will depend on what epsilon and delta are. The closer the delta is to 0, you want count with very high confidence, so you are likely to pay more in runtime. So one question one can ask is, why are we interested in these abstract looking problems? Well, it turns out that there are a lot of applications in different areas, ranging from verification, probabilistic inference, planning under uncertainty. In the world of MOOCs, where you are interested in generating problems automatically, when you have a lot of students, you don't want to give all of them the same problem and get the same answer. So, just to convince all of you that I just did not make up all of these boxes, I'll talk about one of the applications of sampling, which is in verification. So in this, these days all of us carry very complicated devices, and it is very important that the devices adhere to the specifications. This area is called functional verification, where you want to make sure that whatever definition or specification you have given for a device or a circuit, the implementation adheres to it. In case of functional verification, there are 2 ways of doing it. One is formal verification, where you have mathematical model of the system and you try to use mathematical tools to give a certificate that system is correct. Usually what happens in industry is called dynamic verification, which is the dominant approach. how does it work? You start with a design, you simulate with test vectors. These test vectors typically represent different verification scenarios. You see the output and you check against the specification. The big question here is how do we generate these test vectors? Because the space can be really large. So for example, if we have a very simple circuit that takes two inputs A and B and output C, both of these are 64-bit integers, the possible number of things one might have to generate will be 2 raised to 64 multiplied by 2 raised to 64. That's 2 raised to 128. There is absolutely no way that one can go over all of these possible pairs of A and B to test whether the circuit is correct. So in 90s this was observed, and what led to is called constrained random simulation based testing, where you typically put additional constraints. And the key idea behind is you are not interested in trying over all possible values of A and B. You sort of have some intuition where the bug might lie. So these constraints come from variety of sources like designers, experience, and users. I don't want you to read and understand what exactly these constraints mean, but just to tell you that they can be fairly complicated. And the test vectors are the solutions of these constraints. Life would be simple if we could just get all the solutions of these constraints and try on our circuit, but turns out that there are way too many solutions, so we can again try on very small combinations of solutions of these constraints. So the typical way of solving these constraints is using SAT SMT solvers. SMT stands for satisfiability modular theory. SAT is the canonical NP-complete program where given a formula, Boolean formula, you want to know whether it is satisfiable. So there have been a lot of progress in SAT SMT solving, and the idea is let's try to throw these constraints to the solver and hope that the solvers can do a random generation of solutions. That actually does not work. So what finally the problem of that we are interested in is sampling satisfying solution uniformly at random, and this is exactly the problem that I described. We start with a set of constraints represented in the SAT formula or CNF formula, and we want to generate solutions uniformly at random. I hope you see the problem that we have converged on is exactly the problem I described in the first slide. This is also called a scalable uniform generation of SAT witnesses, a slightly long and complicated name. I'll be just using constraint sampling for it. So the first question when we look at these problems is how hard are these problems in theory? Well, it would be very trivial if we could enumerate RF, right? If we can get all the solutions, then picking one randomly out of them is not too hard. But that's almost always impractical, because if you have formula over n variables, you are typically going to have you might have exponentially many solutions to enumerate. So this the problem, the application I was representing there, you typically have about 10,000 variables. So think about enumerating 2 raised to 10,000 solutions, a number I cannot write here. So for counting, the problem interested theoreticians in 70s, and Leslie Valiant was able to show the problem is sharply complete. Sharply is the class of problems that are far beyond NP, far harder. So if you thought that NP is sort of really hard problems, no, they are far beyond NP. In case of approximate counting, Stockman in 1983 showed that it is possible to do approximate counting where the confidence parameter delta set to 0 can be accomplished by a Turing machine that has access to sigma 2p oracle. Sigma 2p is the oracle of the second level of polynomial hierarchy. So the first level is called NP. So NP to NP is the sigma 2p oracle. Yeah.
In verification, generally people are interested in figuring out the witness, right? So what is the motivation for counting in verification?
Counting has mainly applications in probabilistic inference. where given a network, you can reduce the problem of computing the probability of some event of interest to counting over some Boolean formulas. But it actually has one of the applications in case of verification as well. So suppose someone writes a set of constraints and you want to know how many solutions are possible. If there are way too many, there is no point of doing even uniformly random generation, because you will be able to cover only a small part of the space. So this is usually used to determine the coverage of, when you do these random verification steps, you want to know how much space you have covered after a certain time. So you need to know the count. But the big application of this is in probabilistic inference. Again, Stockmer in 1993 asked, what if we introduce randomization? So here, back to the delta greater than 0, it was shown that it is possible to do with access to an NP oracle. I want to stress that NP oracle, I'll be interchangeably using the term NP oracle and set solvers, because in practice we assume that set solvers behave like NP oracle. Theoretically, an NP oracle means some oracle that can solve problems in NP in polynomial time. So we'll be interested in designing these probably approximately correct algorithms for this counting, and going to sampling, how hard it is to do sampling. Well, for uniform sampling, it has been shown that you can again do in polynomial time with a probabilistic Turing machine which has access to an NP oracle. And this was one of seminal paper by Bellare, Petrak, and Godric and Petron. For almost uniform sampling, where we introduced 1 plus epsilon factor, it was shown that this program is interreducible to counting. So pack counting and almost uniform generation are interreducible. This is something that we'll be using later on to design our algorithm. So again, these algorithms are going to be probabilistic. So we want to ensure that the algorithms output something with probability greater than half. Because you can design an algorithm that never outputs anything, it will, and in that case, this condition would trivially be satisfied, because you can say that probability a solution never gets output, so that is not an algorithm of interest. So, since these problems have a lot of applications in different areas, we are not the first people to look at these problems. They are having a lot of work for 3 decades, and I would not be able to go through all of that work. But to summarize, the big problem with the prior work has been either it has failed to scale to large industrial instances, or it provides very weak theoretical guarantees. So since 2013, Moshe Vardi, Supratik Chakrabarty, and I have been approaching this by where we introduced this hashing-based approach to approximate variance of sampling and counting. This we believe has strong theoretical guarantees, and we have been able to show that it scales to large instances. There have been a lot of others in the community who has worked on this and extended it to different dimensions. So let me get into the core of this approach, how exactly we do sampling and counting here. So let's just stick with counting for a minute. So suppose the circle represents the space of all possible assignments and the dots here are satisfying assignments. So we are interested in the problem of counting the number of dots. Of course, I'm sort of simplifying things way too much. This is not how a Boolean hypercube looks like. So the idea here is that what if we could partition the space of all satisfying assignments into small cells that are roughly equal. So what do I mean by small? The number of solutions in every cell should not be too large, so that we can exactly enumerate all the solutions in that cell. And the number of solutions across the cells should be roughly equal, because then we can go and pick one random cell, count the number of solutions in that cell, multiply with the number of cells. give us really good theoretical guarantees, if we can do it. So not surprisingly, the primary question is, how can we partition into roughly equal small sets of solutions without knowing the distribution of solutions? Remember, if you know the distribution, the problem of counting is very trivial. If you exactly know where the solutions are, you can count them. And for this we use one of the classical technique of universal hashing that was proposed by Carter Beckman in 1977. What we show is that there exists very efficient class of universal hash functions that can accomplish our primary task of such a division. I'll discuss later on how exactly these universal hash functions look like, and that will be the core of the talk on improving these further. But before that, I need to answer 3 more questions before I can convince you what needs to be done to improve the scalability of these techniques. One is, how large is this small cell? What do I mean by small cell? Second is, how are we going to compute solutions inside the cell? So suppose I have the cell, how are we going to find all the solutions there? And the third question is, how many cells do we want to partition the solution space in? So the size of cell, we know we don't want it to be too large, because you could have thought of the original problem as the problem with just one cell. It wouldn't work because the number of solutions in the cell could be exponential, so we don't want it to be too large. At the same time, using classical sampling results, you can show that we cannot have it too small. We would want it to be very, very small, but you cannot have it too small because the ratio of variance to mean becomes very high, which typically results in very low probability guarantees. So similar to a lot of classical sampling based approaches, we finally arrive with the definition of small as a cell that has less than pivot number of solutions, where pivot is a function of epsilon. So it is inversely related to epsilon. This sort of intuitive makes sense. If you want count to be very, very accurate, you need to enumerate more solutions. There are no free lunches. So the second is, how do we solve a cell? How do we enumerate solutions inside the cell, right? The idea was that we will partition into small cells. We are going to pick one of the cell and we are going to enumerate solutions inside that cell. We are going to count the solutions exactly. So for that, first let's look at how do we represent a cell. So suppose our formula was on variables x1 to xn. To construct a hash function that maps from the space of 2 raised to n to 2 to n. So here we are interested in dividing into 2 to m cells. We have to choose m random XORs. And how do we choose every XOR? We pick every variable with probability half, and we XOR it with 0 or 1 with probability half. So we might arrive at something like this. X1 where x1, x3, x6 got picked, x2, x4, x5 were not picked. And then to choose one of the cell, we set all of these XORs equal to 0 or 1 with probability half. So what we finally arrive, we have m XORs and all of these are set to 0 or 1 with probability half. The action of setting these to 0 or 1 with probability half exactly chooses one of the 2 raised to m cells. So a cell here represents the original set of constraints in CNF form, and then this extra set of constraints in XOR. At the start of the talk, I mentioned that we will be using anti-oracle. So what we do is that we can give this set of constraints to a set solver that can solve, that can find a solution that satisfies the original set of constraints F and these XORs. To enumerate, once we find one solution, we block it. We say that, give me another solution that is not what you just returned. And this is how we can enumerate all the solutions. And remember, see, this is where it makes sense to have the cell not to be too large, because we will not be able to do this step if we have to enumerate exponentially many solutions. Finally, how many cells do we want to partition into? Well, ideally we want to partition so that all the cells have roughly pivot number of solutions. But that requires us to know RF. Suppose you have two solutions and you want to partition so that all the cells have one solution each. Then you should partition into two cells, right? If you partition into 100, it's not going to work. But if you have 100 solutions, you have to partition into 50 cells. So you need to know somehow it looks like that you need to know what are the number of solutions. But that is very circular, because we started with wanting to estimate the number of solutions. If we have to know the number of solutions, this is not a good algorithm. So to get around this, we propose a search technique where we start with setting m equals to 1, so we partition into two cells. We pick a random cell. We ask if the number of solutions in this cell is less than pivot. How do we do that? We keep enumerating solutions until we go beyond pivot. So if we find pivot plus one solution, we know that the number of solutions is greater than pivot. In that case, we break out of the loop, and that is our desired number of cells. Otherwise, we partition the cell randomly. The cell that we pick right now, we partition into two and choose one of the two cells. And we repeat the whole process until we break out of the loop. Yeah.
How do you pick the pivot? You say it's function of.
So pivot is exactly the definition what we described. Pivot is 5 into 1 over 1 plus epsilon square. One seemingly simple thing to observe here is, if you partition the cell into, so at every step, if the number of solutions is greater than pivot, we partition the cell further. So at no point we will be increasing the number of solutions in the one of the partition, right? You start with something that has 100 solutions. If you partition it further, you cannot have 101 solutions. So what we observe is that there is a monotonicity, and you can do far simpler. You can do something like a binary search here, which allows us to reach an algorithm that makes the number of set calls, because the first line is exactly a set call, and that is the most expensive step. So the number of set calls we have to make is logarithmic in n. Something very interesting to note, remember the number of solutions can be 2 raised to n, right? And we have to make only logarithmically many set calls. So what did this lead to? Using this, we were able to propose the first scalable approximate model counter approximacy, Unigen, that was the first scalable almost uniform generator. And both of these we have shown that outperform state-of-art generators and counters. There have been a lot more being done on these. But one of the questions to ask is, can we do better? And for this, we went back to the core of the whole technique, which is to use these hash functions. So let me describe it again to make sure we are on the same page. Remember, we have variables x1 to xn. We want to partition into 2 raised to m cells. So we are constructing m random XORs. And finally, we are giving input as the original formula conjuncted with this m random XOR. So a quick probability question. What is the average length of each of these XORs? This is not trick question. It is n by 2. Expected average length is n by 2, because you pick every variable with probability half. So half of the variables on average get picked, half of them won't be picked. So something that you observe if you use set solvers is that they don't like large constraints. they like small parity constraints. So parity constraint is another term for XOR constraints. So the set solvers like parity smaller XOR constraints because that leads to better performance. And the question we ask is, can we shorten these XOR clauses? The first idea can be, well, why are we picking with probability half? How about we pick something with probability smaller than half? So the simple approaches actually do not work because these XOR constraints were able to give us something very powerful guarantee that they are able to divide the solution space into roughly equal number of solutions. So there were some attempts by trying to design XOR constraints where you are picking every variable with probability less than half, and all of those have been shown that they cannot provide strong theoretical guarantees that we need. So what we observe is, we are working on this, we are interested only in the solutions of a formula. So think about a formula that is represented over n variables, and we try to define a set, something called independent support, where this set I, which is independent support, is such that assignment to these, if variables that are in the independent support, if once you assign to these variables, rest of the variables can be uniquely determined. So when you would have seen something like this, think of a circuit. Once you give inputs, you can determine everything else that is happening inside the circuit, right? So more formally, if two satisfying assignments agree on the variables in the independent support, then they must be the same satisfying assignment. So suppose we had the formula C if and only if A or B, then the independent support of this formula is A and B, because once you assign to A and B, there is a unique value for C. But A and C is not an independent support. Why? Because you can assign C equals to 1, A equals to 1, B can take either 0 or 1. So when we observed this, we were working on circuit problems where we knew what are the primary inputs to the circuit, what are the input variables to the circuit, and we made the observation that we need to do hashing only on the independent variables. Okay, only on the variables in the independent support, and that can reduce the average size of XOR from n by 2 to I by 2. And our initial observation was that for a lot of problems, it is indeed the case that I is very small compared to n. But we couldn't come up with an algorithmic procedure to identify independent support. So our initial idea was that let's ask the people who give us the problems, primarily if they come from the circuit domain, what are the input variables? And turns out that the seemingly simple question is very hard for people to answer, because by the time they come up with this formula, they have done a lot of steps in their setup where they have modified these formulas through different hooks, and often they gave us the wrong estimate of the independent support. So the issue we had was most of the time we would get independent support, and finally we would get count, they would say this doesn't look right, we would go into observing the circuit more into detail, and finally say, well, you gave us the wrong independent support. So there was no procedure to determine independent support, and our contribution of this work has been that an algorithmic procedure to compute minimal independent support. I'll describe what exactly is minimal. Minimal is one observation is there can be a lot of independent support. We are interested in the smallest independent support possible. We also wanted to analyze. So now we are interested in finding satisfying sigma 1 from here, sigma 2 from here. Remember the difference between satisfying assignments of the formula with xi and yi is that you can always replace every xi with yi and you'll get exactly the same set of solutions, right? So what we say, what the definition says here is that if two satisfying assignments agree on I, so if we have sigma 1 and sigma 2 from here, and they have the same assignments for xi I for i's that belong in the independent support, then they must agree on rest of the variables. Staring at it and doing a small transformation, when you have a constraint of the form A implies B, you can observe that A and not B has to be false. Because if A is true, then B must be true. So A and not B cannot be true. So you can easily state that this formula must be unsatisfiable if and only if I is independent support. One of the direction is slightly tricky, but I will not go into details here. But you can arrive at this theorem pretty easily. So let me try to represent problems slightly differently. You start with a set of these closed HIs, and you have omega, which is original formula, copy of the original formula and the constraint that were coming from the left side. You can rewrite the first theorem to say that if I is independent support, then HI. So take all the HIs from here that where I belongs to independent support. So HI and omega is unsatisfiable. This problem has been well studied in different area of formal methods, where given a formula psi so that h1 to hm and omega, and suppose the formula is known to be unsatisfiable, then the problem of the interest is to find a subset of these HIs such that the subset of these HIs and omega is still unsatisfiable. Finding this subset is called unsatisfiable subset, and if this subset is minimal, then the problem is called minimal unsatisfiable subset. So now, as you can see, I have almost matched all the notations. So it's not surprised that the problem of minimal independent support can be reduced to finding minimal unsatisfiable subset. So our algorithm is going to come up with the basically the set of clauses and the original for the omega here and HIs here, and give it to a solver that can compute minimal unsatisfiable subset pretty efficiently. There has been a lot of work in designing such solvers, so we'll be able to use off-the-shelf solvers. So one question to ask is, what about the complexity? Well, completing minimal unsatisfiable subset requires FP stands for functionally polynomial, where instead of usually we are interested in problems where we want to know yes or no answer, but in these kind of problems we are interested in computation of a function. So the complexity of MES is FP to NP. And essentially we could also show that this is complete for this class, computation of minimal independent support. So one can ask, didn't we start with trying to solve a problem that was in the same complexity class? Remember we were defining that we need a polynomial time Turing machine that has access to an NP oracle. This is the way to denote an oracle. So here we can solve in polynomial almost with abuse of notation. You can think of this as solving in polynomial time given access to an NP oracle. So we were trying to do counting which had the same complexity class, and now what I am defining is that how about we first compute the minimal independent support that again has the same worst case complexity, and then we use this to solve another problem in the same complexity class. So again, first do the minimal independent support computation, then give it to the sampling and counting tools. So this is where I like how if we started basically looking at the problem from very theoretical perspective, we would never have come up with such an algorithm because it makes no sense. Doesn't seem to change complexity of the problem at all. It doesn't seem to improve any of the steps. But what effect does it have on practice? So our hypothesis was that these independent supports are going to be small. So what we did, we took a large set of benchmarks. We have about 300 benchmarks. These are only one subset of benchmarks. And we computed independent support using off-the-shelf MUS solvers because the translation was very simple. It took about 20 lines of Python code. What we see is that, yes, indeed, the independent support are usually 1/10 or 1/100th of the total number of variables. And this takes very little time. So we can run these tools with setting a timeout. If the timeout they still give something that may not have the guarantees of minimality, but is still an independent support. So let's try to combine with these approximate counting and sampling tools. Okay? So how we are going to do? We are first going to take the formula, run on minimal independent support computation tool, and then take the output of this, give it to the sampling and counting tool. So here on the red is the time for approx MC without minimal independent support, and green is the time for approx MC, which includes the time to compute the minimal independent support and do the rest of the counting. Okay? So in both the cases, we give the tools the original formula and finally we wait for the time when we get the count. So 18,000 was the timeout, and what we see is that this seemingly idea of where we are not able to reduce the theoretical complexity works really wonders in practice. We are able to solve problems that we were timing out earlier, and now we can solve them far quicker because here for most of these problems, even after 18,000 seconds, we did not have the count, and now we can indeed have the count for these problems. So how does it impact the sampling? We observed a similar effect again. For a lot of problems where the sampling tools were timing out, we can solve them far, far faster. Remember, this includes the time to compute the independent support. So to summarize, sampling and counting are fundamental problems in AI, which has a lot of applications. And what we have observed is that independent support is key to scalability of these techniques. Here we propose the first algorithmic procedure to determine independent support, and in practice we typically see about 1 to 2 orders of performance improvement in sampling and counting tools, which include the time for computation of independent support. So with that I will conclude, and I will be happy to take any questions. Thank you.
So going back to previous slide, so what is your definition of scalability?
Scalability we measure in two ways. One, take the similar formula and try to see if we get larger number of variables where we are encoding the similar circuit. Can we scale to large formulas? The other is a very similar definition, is what are the how big formulas can we handle. So before independent support, some of these formulas that I was showing, before we use this notion of independent support, we could handle about formulas with about 10,000 variables, and now we can handle about 500,000 variables.
So you mean in the same time?
Same time, yeah.
What about space? Like, are you constrained by space?
No, typically most of the space is consumed by the set solver in the rest of the. Once you give the independent support, most of the constraint actually comes from the set solver running. If you ask that why set solvers were not able to handle earlier with large number of large XORs, then they do get constrained by XOR by the space, because you have about 500,000 size XOR constraints, which are, and you put about 50 to 100 such XOR constraints, which become very hard to do all kinds of, there are a lot of steps in the set solving, which get greatly reduced if you put only 1,000 size XORs. So all the matrix representation and all becomes far simpler.
So the MIS algorithm, you're running that on the full original problem size, like length and problem size, right? Do you have any idea why it's running so fast, given that the complexity is just as bad as the full problem?
I think this sort of has throws light on worst case complexity analysis that is probably not a good. What we see again and again is not good enough to predict the performance of runtime performance. So one nice thing, of course, I am not claiming that you can give it as large formula as possible and it will always complete the independent support. So we do run all of this with timeout. There was actually one of the benchmarks, if I can remember, there is a squaring one benchmark where the MIS algorithm times out after 300 seconds, but it is still able to give an independent support that is smaller compared to the original set of variables. So of course, it is possible that in worst case it still has the same complexity, if p not equals to NP. But in practice, the problem seems to be far easier than counting. And the reason I said that it has the same complexity as sampling and counting, because sampling and counting has not been shown to be complete for the complexity classes. So which would be even more surprising if we are able to bring down sampling and counting, and MIS is shown to be complete. So this would probably shed more light on why the worst case complexity analysis is not sufficient.
So this is again just related to Jonathan's questions, also comments. So a lot of the benchmarks you have are about arithmetic manipulation, bitwise arithmetic manipulation. So it's easier to represent the Boolean, the resulting Boolean function as a circuit. And when you really say MIS, it's somehow related to the structure of the circuit. So how related is the structure of the circuit to, so what happens if you have a formula which does not have a very good circuit representation, which may not exploit the independent support property as well?
So that's a good question. There are two points I want to make. First, there can be a lot of independent support, even for a circuit. Primary input, the inputs to the circuit are one possible independent support. There are actually a lot of different independent support, because by definition, at no point you are implying the direction sense you can think of. For example, if you have an XOR circuit, where X1 and X2 are input and X3 is output, any pair of these three variables is actually an independent support. So when you run MIS on even the benchmarks which have very nice representation when we start with, you typically get independent support that is not always the original input variable. So you tend to get independent support that is scattered around. We did some experiments where it does, so one can ask which independent support to choose. If you have a lot of independent supports, which one to choose? And we did some experiments where it seems like if you choose independent support, if it's a circuit, So when you have input variables, there are a lot of what is called intermediate variables and then output variables. So it seems to improve performance when the independent support is scattered around. If you are trying to represent this in the circuit form, so the independent support that is scattered around seems to improve the performance. We don't have any theoretical scale to say why. So we had a lot of benchmarks which came from graphical models, which has absolutely no circuit representation, a good circuit representation to start with, and it performs equally well on those.
Is there any correlation between the size of minimally independent support set and your performance improvement?
So in general, it works well when the independent support size is smaller, but it's hard to say whether, let's say you have two independent support, one of size 55 and another of size 50, which one will be better is hard to say, but it is certainly going to, for at least for all our experiments, when you have independent support of size 50 and original set of variables like 5000, then 50 is always far better than 5000, but if you have 50 and 55,
Question. I'm not an AI expert, but I'm just curious to know that where does this count? Can you give us a scenario in AI where this counting helps?
so one application that I talked about is you start with a graphical model. So the classical example is, you know, you have an alarm system and you want to know if alarm rang, whether it was a false alarm or not. So what you can do is you can represent a formula that describes the dependency between different events like earthquake happening and alarm ringing. And then for every conditional probability table, you can again represent that as a formula that so that all the probabilities, because probabilities are in frequentist sense are exactly the count of events, right? So probability can be represented as count of some events of interest. And then when you are computing the probability of some event of interest given evidence, the problem reduces to the count. There's another application that we just submitted to one of the AI conferences, Triple AI, where you can show that the probability of computing whether there will be a blackout after a hurricane disaster can be reduced to problem of counting. And there we were able to show that all the other approaches take about a week to return answer, and approximately with independent support can do it in about 40 seconds. Thank you, everyone.